Welcome back, statisticians, to our second review session, this one being on designing studies and experiments. So the first thing that we're going to do is take a moment to look at these four different situations, choose one of them, just one, and design an experiment or study to answer the questions. So maybe you choose number 8, sodium nitrate is often added to lunch meat and hot dogs to fight harmful bacteria. What long-term health effects do nitrates have on our health? If you were to choose this one, design an experiment that would help you answer this question. While you're designing the experiment, think about whether or not this is an experiment or an observational study. How do you know? What's the explanatory and response variables? Exactly how will randomization be used? Why do we need it? Is a control group necessary? Why or why not? And would blocking be a good idea? Why or why not? So take some time to do that before you go on in this video. So go ahead and press pause, take your time, design the experiment based on which one of these four you choose. And how are you going to design that experiment to answer the question that you have chosen to investigate? All right, now that you've had a chance to design a study, going back to those questions on the previous screen, why do we need to incorporate randomization or random assignment to treatments? That's to reduce bias. For example, if we want to know the effects of exercise on overall health, and we allow participants to go ahead and self-select into either the exercise group or the control group, the problem is that we're going to have those people who maybe regularly exercise go into the exercise group, and those who regularly don't go into the non-exercise group. And the problem is there that it's possible that there's something about those who choose to be in the exercise group that already put them in better health overall than the group that doesn't exercise. So we just want to that would introduce bias, and so we randomize random assignment to treatments in order to reduce bias. Is a control group necessary, and why? A control group helps us reduce the effects of confounding variables. Using a control group means that any change in the dependent variable can be attributed to the independent variable. So, for instance, if we go back to the previous example where we were talking about exercise and non-exercise groups, that non-exercise group, that would be the control group. And if we didn't have that control group, how would we know whether or not the exercise was actually having an effect on overall health? So again, it's to reduce the effects of confounding variables. It's possible that maybe it's the diet of the exercise group, or maybe it's the fact that they regularly see the dentist, or maybe it's what they do for a profession that helps them with their overall health and not the exercise itself. So when we do an experiment, we really need to separate our treatments and include a control group just so that we can reduce the effects of confounding variables. We don't want those other things getting in the way. We want to know for sure that exercise is what leads to better overall health. And then would blocking be a good idea? Why or why not? Blocking helps us reduce variation so that we can really see how well the treatment affects the group. We saw this in the dog blocking activity where you were all assigned a dog or 2 or 3 in some cases. And blocking by breed helped us reduce the variation within each treatment group. All right. So you can see that we've got a lot of vocabulary here. So first we have to decide how we're going to choose the subjects or the experimental units, and then we have to decide how they're going to be assigned to treatments. So some of the ways that we choose our subjects, simple random sample is the most common. We see that as SRS on some of the problems in our textbook, and also you may see that on the AP exam. That just means that every possible group of a particular size is equally likely. An example of this would be that we take everybody's name who's an 11th grader, and we drop all those names into a hat, we mix it up, and then we pull out 20 names. That's going to ensure that every group of 20 that's possible from the population of all the 11th graders is going to be equally likely to be chosen. Stratified random sample, that's where we separate experimental units, subjects, whatever, into separate groups first, and then we draw an SRS from each one of those groups. So an example might be that we go by grade level again. If we split everybody up into 7th, 8th, 9th, 10th, 11th, and 12th grade, and then from those, we go and take a simple random sample from grade 7, and maybe we select 10 people, and then we go to the grade 8s, and their names are all in a hat and all mixed up, and we choose 10 names there. And then we go to the 9th graders, and we put all their names in the hat, and we mix those up, and we choose 10 from the 9th grade, and so on and so forth. So it's breaking up the population into strata or into like groups, and then choosing an SRS from each of those groups. Systematic random sample, that's like choosing every third person. Okay, if you can imagine when often, I don't know if they still do it, but in PE, when I was in school, we would often be asked to line up in a straight line and then count off in groups of 4. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and so on and so forth. All the 1s would go together, all the 2s, all the 3s, and all the 4s. A systematic random sample might be that you count off like that, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and then you just choose the 4s, let's say, to take part in your study. A cluster sample, I think we might have talked about this in class. If you wanted to take a sample from an orchard, a sample of apples from an orchard, a cluster sample would be like you randomly select 3 trees, and then you take all of the apples from those 3 trees. So you break up the population into these clusters, and then you, in essence, take a census of each of those clusters. You take everyone from the cluster. Voluntary response sample kind of goes along with what you think it would be. You're going to do an experiment or do some sort of study, and you ask for volunteers to take part in your study. And then a convenience sample, that's like me asking just the students in the front row because they're conveniently located close to me if I were standing in the front of the room. All right, and then so once you've got your subjects or experimental units, how are you going to assign them to treatments? So we're going to do that either by a completely randomized design, a blocked design, or a paired design, sometimes called a matched paired design. So a completely randomized design, that means that maybe you assign everybody a number, you put all those numbers into a hat, everybody gets a unique number, you put all those numbers into a hat, and then you randomly draw out half of the numbers, and then those folks will go into one group, and anyone left in the hat will be in the other group. So that's a completely randomized design. A block design, we often see studies that are blocked by gender. So maybe we first divide the population into 3 groups, those who identify as female, those who identify as male, and those who don't identify in the binary system as we have it. And then from there, they're completely randomized into the different treatment groups. So first they're separated by gender, and then they're randomly assigned into the treatments. And then a paired design, this can look a lot of different ways. It's possible that you could, like a pre-test and a post-test, that's where the same person is getting both the first treatment and the second treatment. Sometimes we see that in a medical study where maybe for 6 weeks you take one drug, and then record your results of, let's say, your blood pressure. And then for the next 6 weeks, you take a different drug and record your blood pressure at the end. And you would have been randomly assigned to determine which one of those treatments went first. So that's a situation of paired design. Another one might be that you're testing tires. You might take a particular car and put maybe Michelin tires on the right side of the car and another brand of tire on the left side of the car. So it's possible that you're doing sort of both things at once. You have both kinds of tires on the same car. So many different ways to get that paired design. Another one that we saw, I think we did this activity in class, had to do with cholesterol. And we matched up 2 people who were of similar weight. And then we can flip a coin and put one person in one treatment group and one person in the other. Oftentimes they'll do studies on twins because twins are so similar. That you can get 2 people who are similar to each other by genetics that way. And then you can flip a coin. One twin will go into one group and one twin will go into the other group. So that's paired design or matched pairs design. So a lot of vocabulary here to look into and work through if you're not feeling really confident on some of these. All right. Then what are we going to do? Once we've got our subjects, we have to decide, are we going to survey them? Are we going to do an observational study? Or are we going to do an experiment? If we survey them, we have to pay close attention to how we word the questions, who's going to ask the questions. If you can imagine, I think we talked about this in class as well, maybe you want to survey folks on a college campus about their use of marijuana. If you have a student asking the question, perhaps people are more likely to tell the truth. Whereas if you brought somebody, you know, an 80-year-old who looks like your grandmother, and she was asking the questions, maybe kids would be more apt not to discuss. If they were users of marijuana, they might not say so. An observational study is what you think it is. It means that we are not, you know, imposing a treatment on anyone. We're just sort of watching. Bird watching might be an example. Some of the stuff they do out at the nature center with the owls, they sort of observe whether or not the tagged ones come back each year or something like that. So you have to decide what data you're going to collect and then whether or not that's categorical or quantitative. But remember, you're not imposing a treatment. An experiment is really reserved for imposing that treatment. And once you've decided to use an experiment, there's a whole bunch of vocabulary again here that you would have seen on the first thing. If you had picked one of the questions that would be best answered with an experiment, you might have already been thinking during this review session about explanatory variables and response variables. What treatments are you going to use? Whether or not there's going to be a placebo, whether or not there's blinding. Remember, blinding is that the person participating doesn't know what treatment they're getting. So that wouldn't work very well in the instance of the exercise and the non-exercise, but it might work well if you're using a medication and you can make that placebo look identical to the medicine. Let's say they're in pill form. It would be easy for the researcher to know which drug is which, but not the person necessarily who is participating in the study. Double blind means that the researcher always knows, but that the person who's administering the drug, even the nurse who comes in to maybe give you the pill, doesn't know, as well as you don't know as the experimental subject, which treatment you're getting. So there's two people involved there who don't know. That's what makes it double blind. Not only does the experimental unit or the person participating not know, but also the person who is actually physically handing them the treatment or the drug also doesn't know whether or not that's a placebo or true medication. And then the control group, we've talked a little bit about that. All right, so the next thing that I would want you to do is attempt the first 6 multiple choice problems. We're gonna show you real quick. New share here. Let's see if we can get to this. So the section that I'm working on in your handout, your review handout, starts here with designing studies and experiments. And if you flip in a little bit, you'll get to the multiple choice questions. The first one has to do with a large company wants to conduct a survey to determine the proportion of its male employees who practice yoga on a daily basis. So if you can find this page, you'll know that you're in the right spot. And I'm going to give you, if we were in person, I would give you about 12 minutes. You generally get 2 minutes per multiple choice problem. There are 40 questions and you have 90 minutes. And give or take, that's about 2 minutes per problem. It also gives you a little bit of time to enter your answer onto the Scantron sheet. So for these first 6 multiple choice problems, just the first 6, 1, 2, 3, 4, 5, and 6, you give yourself about 12 minutes. So pause this video, give yourself 12 minutes, give those problems a try, and then come back. All right, welcome back. So here are the answers to those 6 problems. Number 1 is A. This is very similar to a problem we did back in 2002. Since a random sample of the regional offices was taken and then a census of the 2 offices selected followed, this is an example of a cluster random sampling. So the regional offices, they operate like these clusters. And then from the regional offices, 2 of them were chosen. And then they went into those regional offices and they actually surveyed everybody in those 2 offices. So they did a census of the 2 offices. So that's a cluster random sampling. In question 2, the answer is D. In an experiment, random assignment of treatments controls for other variables resulting in an ability to conclude cause and effect. We talked about this in class as well. All right, number 3 is C, similar to a problem from 2007. The survey uses voluntary response and is not an example of a stratified random sample. 3 more to talk about here. Number 4D, similar to a problem in 2007. Blocking by engine size creates homogeneous groups since the size of the engine is known to affect the engine life. It's known to affect. You want something that is known to affect. So if we go back to that dog blocking activity, we knew that the dogs in each breed were very similar to each other and that that had an effect on their bone density. So we already knew that the breed had an effect on bone density, and that's why we blocked by breed to reduce variability. Okay, so that's what's happening here. We know that engine size affects the engine life. So we're going to block by engine size to reduce the variability. Question number 5, D as in dog is the answer there. Similar to an AP course description problem, not off an actual exam. If those that don't respond are similar with respect to income, this will cause the estimate to be biased. So we've got that non-response bias going on here. And of those who are not responding, if they are similar in somehow, then if we actually were to get them to answer the question, they would answer the question more closely with each other. And that would change the results of the survey very much. So again, that has to do with whether or not that group that didn't respond are similar in somehow. That's going to create bias. And then in number 6, E is the correct answer. It's similar to a 2002 problem. Since the group wants the best overall comparison, a matched pairs design is the best. If you said D, like I did, just keep in mind that matched pairs design is very good for best overall comparison. Okay, if you think about this is the mosquito problem. So if we randomly assign folks into 2 treatments for the the one spray that has the DEET in it and the one spray that doesn't. Even if we randomly assign folks into those two groups, it's possible that maybe this group has more women in it than this one does, and that the mosquitoes are more apt to want to chew on the females. Maybe their blood is somehow, you know, sweeter or something. Or maybe it's possible that we randomly assign these folks into the two groups and we get lots of younger folks in one group and older folks in another, just by random assignment. It's possible that maybe those mosquitoes like to chew up the young people more. I think I definitely got more bug bites when I was younger, but maybe it's because I didn't have enough bug spray on. I don't know. But anyway, if you said D, don't worry about it too much, but just keep in mind that match pairs design is often underrated and underutilized, and it is really good for making best overall comparisons. All right, so at this point, I would answer any questions. If you have some questions, you can shoot me an email or we can discuss it in class the next time I see you. My suggestions are that you complete the remaining 3 multiple choice questions. So there are 9 altogether, and we just did the first 6. So 7, 8, and 9. And then also complete the free response from 2004 exam regarding shampoo. And I'll just show you where to find that. So these were the multiple choice questions. We did the first 6. There's the other 3, 7, 8, and 9. And then if you turn the page, there 2004 question number 2, researchers who are studying a new shampoo formula plan to compare the condition of hair for people who use the new formula versus the current formula. So give that problem a try as well. And go ahead and pause the video while you finish those 3 multiple choice questions and give that free response question a try. And then on the back end of these slides, I've got the answers to those. So go ahead and pause now, try those, and then come back and get the answers. All right. So for those 3 remaining multiple choice questions to problems 7, 8, and 9, number 7, the answer is E. A stratified random sample creates homogeneous groups based on some characteristic that affects the response variable. Number 8, D, because both groups were given a similar looking candy and knew the experiment was being implemented, the placebo effect may have improved the results of the non-peppermint group there. And in number 9, the answer choice is B. Results can only be generalized to the population that was studied. All right, because no other ant species were part of the experiment, we don't know about those other species of ants. We only know from the population that we took. All right. As far as that free response question goes with the shampoo, here's the solution for part A. This is taking into account age, but not gender. So you can see we're taking the 2 youngest here and putting them in one block, and then the next 2 youngest, and the next, and the next, and the next, until we get to the oldest group being in that block 6. And then in part B, we believe the condition of hair changes with both age and gender. So we're taking both of those into account here. So we've got the female who are the youngest females, the middle females, and the oldest females. And then we've got the youngest males and the middle males and the oldest males. So now we're blocking by both gender and by age. And you can see how that's scored here down below. Both parts A and B are scored as essentially correct or partially correct if either component 1 or 2 above is correct. And then the last part C solution here, the answer is no, but you really need to explain why. And down here, we've got the scoring guidelines for how to get an essentially correct answer. The student needs to recognize that this is not an appropriate way to assign treatments and describes an appropriate method for assigning those treatments within each block. All right, and that's the end of our session. So thank you for taking the time to give these problems a try and join me for this review session. I look forward to the next one. Take care.